Hello everyone, my name is Omar Navarro Leija, and today I'll be talking about Dettrace reproducible containers. So first I want to start by talking about why reproducibility matters. So as programmers, we end up making assumptions about that programs are deterministic or reproducible when they execute. So let's look at a few examples where we kind of assume these things. So for scientific computing, for science to work, we want experiments to be repeatable. So we assume that scientific software is going to be reproducible and repeatable when we run it. Similarly, for security, one example we'll be looking at throughout this presentation is reproducible builds. And we'll see how that works more in a second. But similarly, here you assume that when you build a program, the output binary will be the same, given that the source code hasn't changed in any way. Similarly, when we talk about software engineering, reproducibility and determinism are really nice properties to have. It makes debugging easier, as well as just understanding and thinking about what your program is doing. So one of the problems is that when these assumptions fail, it leads to really hard to reproduce bugs, as well as errors. So one example is a lot of software will want to cache some data, and again, that's an assumption about the program being reproducible or deterministic when it's being cached. So I want to focus on reproducible builds here, and there's this Reproducible Builds project that very much focuses on tackling this as far as software builds goes. So let's look at this quote real quick. And it says, reproducible builds are a set of software development practices that create an independently verifiable path from source to binary code. So the idea here is that most of us are not downloading source code and compiling it ourselves. For dependencies and everything else, we download precompiled binaries or packages containing the code into our systems using a package repository. So the problem here is you may trust a package repository, but what if you're not sure about a third-party package repository, whether that code that has already been compiled has been tampered with or has been injected with some malicious code? So the idea here with reproducible builds is if software builds the same way every time from source code to binary, then what we can do, we can hash that binary to get a unique identifier representing that code or that binary. And then when I download code from another package repository, I don't have to trust that person giving me this code. I can just hash their binary myself and make sure it matches the canonical hash that has been published by some trusted source saying this is a trusted code. So the other thing I want to point out here is this, it's bolded, software development practices. As we know with best practices, it's often a best effort, and developers may not always get it right, and this is not something that's easily automated or checked all the time. So this is one of the problems that we also want to tackle. So now I want to talk a little bit about our previous work in this area. So the first two systems we see listed here, the Terminator and DOS, are both operating systems. And the idea is that they build an operating system that will make sure that things run deterministically. For this latter two works, this is very common of the research in this area. We see D-threads and a deterministic multi-threading deterministic paper as well. So what we can gather from here is that a lot of previous work has focused solely on determinism, and oftentimes previous work focuses on threads interactions with shared memory, which is often what people think about when they think about non-deterministic results from a program. So I've been using a few of these words, and I kind of want to give more precise definitions so we're on the same page about what we're talking about. First, determinism. We're going to say that determinism is on the same machine. When we run a program multiple times, each memory load returns the same value on every run. So notice here there's a few things. In the paper we refer to this as data flow determinism, or I like to think of it as observable determinism. Meaning if you treat the program as a black box of inputs and outputs, given the same inputs, you expect the same outputs every time you run this. Notice this notion has nothing to do with time. People often ask me if we guarantee any sort of deterministic timing of how long a program takes to run, and we do not. Our guarantee here is going to focus solely on data and what's observable. A stronger property than determinism is going to be portability, and we're going to say this is determinism extended across different machines. And when you have determinism and portability, this is what we'll refer to as reproducibility. So one of the key contributions of Dettrace versus previous work is that we move beyond just determinism and we guarantee reproducibility, which no system has done before. Similarly, we're going to move past just shared memory and we're going to look at system level sources of non-determinism. So some that are probably obvious to you are things like time and randomness. But in practice, lots of other things end up making software reproducible. Some examples are file system metadata, such as inodes, modified times, or reading from system-level directories like /proc, unique identifiers like UIDs and PIDs, as well as timers or signals or other asynchronous interrupts that come your way. So now I want to focus about what we did. So the question is, what is Dettrace? And Dettrace is a container abstraction and dynamic determinism enforcement system. And importantly, Dettrace is the first system to automatically handle all sources of irreproducibility for arbitrary programs. So we wanted to make sure Dettrace was a realistic system that you could run and do useful things with, not just an idea. So we spent a lot of time working on the both design and the engineering constraints we wanted to work within. So some examples here is we make sure that Dettrace runs in user space. We didn't want to have to modify the kernel or add any kernel modules or anything else like that. And similarly, we didn't want to assume anything about availability of source code or being able to modify the program. So Dettrace works entirely in user space for arbitrary x86 Linux programs. This all works just in stock Linux. Similarly, we wanted to make sure Dettrace could combine well with existing technologies. So you can use any system image like a Chroot, or you can use a Docker container, and Dettrace nests with them perfectly. So I want to talk a little bit about how Dettrace actually works. So the idea is that programs are deterministic until they interact with the outside world. So what this means is that we're going to catch system calls, which is one way that programs interact with the outside world. So all non-deterministic system calls are caught by our system using ptrace. This is why one of the reasons it's Linux-based. And similarly, the other way you can get non-determinism or reproducibility is via CPU instructions. So what we're going to do is there's hardware support for intercepting some CPU instructions like CPU ID and RDTSE that are neither portable, not or deterministic. But what do we do about system calls that are not being able to be caught by hardware? So when we catch CPU ID, we get an interrupt and we're able to emulate it for that program. So a program is supposed to check when using RDRAND or RDSeed if those are available in that chip. And they do that through CPU ID. So if a program were to ask if there's RDRAND in the system, we would catch CPU ID and say that there isn't. This is not supported on this chip. So a well-behaved program should not use these instructions. Of course, an adversarial or badly written program could still attempt to execute these instructions, and that's something that we don't handle. We don't assume adversarial cases for Dettrace. We assume well-behaved programs that are trying to do the right thing and not going out of their way to be non-deterministic. So similarly, we end up implementing our containerization using Linux namespaces and Chroots. And this is mostly to kind of isolate a lot of the non-determinism coming from the file system without us having to intercept all these system calls that talk to the file system. So it's a lot cheaper to do this way. And similarly, we're going to impose a deterministic scheduling for your program. So we're going to serialize all system calls so the ordering is reproducible every time we run this program. And we're also going to serialize thread execution within a process. However, we know parallelism is important, so system call-free regions across processes can still run in parallel. And we'll see how this works out in our results evaluation. So let's look at an example of an irreproducible program to kind of get a sense of what happens. So imagine we have a process P1 and another process P2. And P1 is going to read the time, and it's going to write it to a file called results.txt. P2 is going to read from a file called /dev/random This is a system-level file that contains random bytes of information that programs can use as entropy for seeding their pseudo-random number generator or whatever they need random data for. And similarly, this program is going to write this to a file. So we can see that there's a few sources of non-determinism here. Reading the time is, of course, non-deterministic, and so are reading this random bytes of data. So notice this is going to, we also have a non-deterministic race here. Depending who gets to write to the file first, P1 or P2, we may see different results every time we run this program. So now let's see how Dettrace handles all this. So here we're going to have we're going to run everything under our container. So we again have P1 and P2, but we're going to add now a third process called the Dettrace tracer. And when P1 attempts to do a call to time, the Dettracer is going to intercept this. And similarly, as we'll see soon, when you do a write, it's going to have to go through the tracer. We'll get back to that in a second. Here, when we read from this file, we're going to, instead of reading from the actual system file, we're going to read from the file implemented inside our container, which is connected to the tracer via FIFO. So we're actually going to be able to decide what bytes this process ends up reading, and we're going to be able to give it some pseudo-random bytes that is reproducible every time we run this program. Similarly, how do we handle this two processes racing on this file? And what we're going to do here, as I talked earlier, we're going to impose a deterministic process scheduling to make sure that they always write to this file in the same order. So now I want to talk about exactly how we verify that something is reproducible. And as far as reproducible builds goes, we're going to use a tool called Reprotest. And the idea is that Reprotest is a tool to exacerbate the amount of non-determinism in the environment. And it's going to do this by varying certain things. So there are specific things that in practice are known to cause builds to be irreproducible. And these are going to be called variations. And here we see a few variations listed, such as environment variables, time, build paths, number of CPUs, and a bunch of other stuff. So when we want to build a package and produce an output, which we'll call the build artifact, we're going to hash that build artifact, and that's going to give us a unique hash representing the bytes inside of this build artifact. We're going to run this twice. Once we're going to call it control, which has no variations at all. And we're going to run this again, having Reprotest vary the environment in all the ways listed here. And this is going to produce two hashes, and we're going to compare these hashes. If the hashes are the same, then for this given run, we don't really know anything. But if the hashes are different, it's going to be irreproducible. So this is how you can gain some confidence that a package is reproducible if you end up getting a hash every time given n number of different variations. So now I want to talk a little bit about what our evaluation was. Similarly, for our evaluation, we wanted to make sure that Dettrace worked on a wide array of programs and solved many different sources of non-determinism. So we didn't want to just cherry pick a few benchmarks and see if those worked or not. So instead what we did, we're going to use Dettrace and Reprotest to build all packages inside the Debian repo for Debian Wheezy. So if you know anything about Debian versions, Wheezy is pretty old. It was old when we started, and it's very old now. So why did we use Wheezy? And the idea was that the Debian Reproducible Builds project has been working on a long time, making a lot of these packages reproducible. So we wanted to go back before those efforts started to make sure we had the most number of irreproducible packages that we could try to make reproducible to make sure that our system could handle all those cases as well. So one thing to note, by default, when we ran this experiment without using Dettrace to see how many packages were irreproducible by default, we saw that all of them ended up being irreproducible because tar actually inserts the modified times into dev packages, and that makes the bits look different when you hash it. Of course, we fixed that, and once you get around that, you see that 72.65% of all packages on baseline, that is no Dettrace, are irreproducible. So our main result is that using Dettrace, we were able to guarantee reproducibility for 100% of all the packages that we support. That's over 12,000 packages that we were able to run, execute, and build inside Dettrace and make reproducible. So one of the keywords in that sentence, though, is supported packages. So there's a few things that we don't support. So here we say that we were not able to build 2,000 roughly packages due to known limitations in our implementation. So we're actually not able to handle busy waiting threads, and we also don't have a good user story for networking. And a long list of other things that we don't handle. I encourage people to see the paper for all the things that we currently don't handle. So now I want to talk a little bit about our overhead. So the overhead of Dettrace is largely determined by two things. One is the number of system calls we have to intercept. Intercepting system calls in ptrace in Linux is pretty slow. And the other thing is the amount of thread parallelism in the program. So let's look at our evaluation here and kind of see how this actually plays out in practice. So package builds are single process, but both system call and IO bound workloads. You might be surprised that I call package build single process, but when we did our evaluation, we found that allowing them to run in parallel versus pinning them to a single core didn't really make a difference, since most of these package builds build sequentially anyways. So package builds actually represent one of the worst case scenarios for Dettrace, since system call interception is so expensive for us. So here we're going to see an average slowdown of around 3.5x. So now we moved on to seeing how thread parallelism is handled by our system. So here we took two TensorFlow programs, AlexNet and Cephar10, that are both thread parallel, but mostly compute bound, so they don't do as many system calls. And of course, sequentializing thread execution is very expensive since we're missing out on that parallelism. So compared to a threaded parallel execution, we're going to see 17.5 and roughly 12x slowdowns here. But if you notice, when ran sequentially on a single thread, we're only now having the overhead of system call interception. And for these compute-bound programs, we see 1.5x and 1.0x slowdown. So that's a lot better. Finally, the best case scenario for us is when we have process parallel compute-bound programs, and bioinformatics workflows often fall into this category. So for example, our best program was this cluster program, which we only saw 1.20% slowdown, given running this with 16 processes. So as I talked earlier, we still allow processes to run in parallel in the regions where they're not executing system calls. So this works very well for programs like cluster that are very compute bound. And as you see, our performance scales with the number of processes added. So now I want to take a few minutes to show a demo of our system. So running Dettrace is as simple as running the binary followed by the program you want to run. So here, if we do an ls on this directory, we see that the user for all these files is set to root, and we also have normalized the time for all these files to a default date. So here we're going to do a stats on a Docker file. And similarly, we're going to see here that the user IDs, the access modified and change time, as well as the inode and other information has kind of been zeroed out by us and given some deterministic reproducible value. So this is how we handle a lot of the metadata coming from the file system. Lastly, I want to show an example of this program called race.sh. And if you can see here, it basically is going to spawn two processes. One process is going to print A's. The other process is going to print B's to the screen. So let's see this first running non-deterministically. And as you can see, the A's and B's change every time I execute this program based on how they're scheduled. Running the same computation now under Dettrace, we can see that the order is always A's first, followed by B's first. And what ends up happening here, our scheduler is able to realize that it's able to run A all the way and then run the B program all the way. If there is blocking system calls or other things that require a program to wait and let somebody else, another process run and come back, our scheduler is able to handle all that. So just to conclude, Dettrace provides a new reproducible container abstraction. And we're able to automatically make arbitrary computation reproducible this way without making any changes to the hardware, the OS, or the application code. There's a lot of details I couldn't go into in this presentation, so I definitely recommend you check out the paper as well as the repo for Dettrace, which you can find here. Thank you.